Welcome back to Clipboard Electronics, and I know this video has been a long time coming, and I know that some people have been waiting for it, but wow, have I been busy. Here you can see the prototype for the Z80 Retrocomputer, and it's running a little bit of machine code. That's why I'm getting some funny blinking here, and it's not just counting through addresses anymore. I have it running at, let's see, 200 kilohertz right now. And I've discovered that there's a little bit of an issue with this square wave that I'm getting. So I may do some updates to the hardware to kind of straighten this out here. But for a testing clock, it's working okay. So I'm going to go ahead with the video about how the ATTiny timer system works and how I use that to create a very fast running clock with the ATTiny 85, and I'll go through a little bit of an explanation of the code. So I know this is going to be a long journey, but it's really important to stick with me all the way through, because it's one of those things where the beauty of the journey kind of comes out at the end. It's like doing a really beautiful mathematical proof. Stick with me, let's get into the hardware diagram, and let's see how this monster works. The way that the timers work on the ATTiny and on some of the other Atmel chips is a little bit difficult to explain, but if you look at the block diagram of the hardware, it makes a little bit more sense, and some of the terminology that we use in the coding of this makes a little bit more sense once you understand this. So let's take a look at that real quick. As you know, a microcontroller like the ATTiny 85 is an entire computer system on a single chip. It has a CPU, it has input-output ports, it's got some memory, it's got a clock, and then over here it's got these timers. These timers are a little bit mysterious to some people, but they are a separate unit from the CPU, and they can kind of sit out here and do stuff all on their own. So normally when you're running a sketch or something, you have the program instructions coming from the flash memory into the CPU where it'll be executed, and then the CPU will read the next instruction from the flash memory, right? It may cache a block of flash memory over here on the CPU so that it can do that a little bit quicker. But the point is, you've got to read the memory and put variables out to the RAM and do a lot of back and forth with the CPU if you want to run code on the CPU. So if I want to get a 1 megahertz signal out of a 16 megahertz processor, right? I got a 16 megahertz onboard clock in the ATTiny 85. I would need to have some routine that only took 8 clock cycles but could toggle the pin. It would be very difficult to write that and have it run reliably. No matter what you do, if you run a sketch, you're not going to be able to switch pins that fast. So these timers, which also have access to the I/O pins, essentially run directly off the clock, and they don't go back and forth with the memory or the CPU most of the time. Now the CPU can set registers in the timers, and we'll look at that in the code, and that's how you tell the timers what to do. Turn them on and off, and generate various signals. But for the most part, these timers just sit over here and do their work on the I/O pins independently of whatever the CPU is doing. So that is why this timer, when you set an interrupt on this timer, it's called an external interrupt, because it is external to the CPU. So don't let that terminology confuse you. This timer interrupts the CPU. That is an external interrupt that came in from the timer. Same as if it came in from an I/O pin. Alright, one good way that I think to understand how this hardware works is to sort of go through and build a block logic diagram of how a timer with the features that I'm interested could work. Now, it would be interesting to see if someone could build this from 7400 chips, because I think it wouldn't be difficult. I didn't do that because I think the block diagram explains it better. Now, one of the ways that as a computer programmer and an engineer, I always try to think about things in terms of input and output. How do we get from input to the output that we want? And in this case, the input here is obviously the clock. So we'll put that up here. This is the onboard clock from the ATTiny 85 or whatever Atmel chip we're running. And in this case, it is a 16 megahertz clock. So let's write down 16 megahertz here. So this thing has an output signal, which is right this. So we have a 16 megahertz clock signal. And the first thing that this goes into is what we call the scaler. So the scaler this is essentially just a binary counter. So one thing that is sort of a side effect of a binary counter is that it works as a frequency divider. So if I put the bits of the binary counter here as outputs, let's say there's 4 bits here. Right, so this could be a 4-bit binary counter, which is available as a 7400 if you want to get that. But if you have a 16 megahertz clock input to a binary counter, bit 0's output is going to be 8 megahertz. Right, because bit 0 flips every other time that the clock pulses. Alright, it counts clock pulses. So this clock pulse comes in, bit goes from 0 to 1. Right, this clock pulse comes in, bit goes from 1 to 0, and the next bit flips. So the next bit's output here is going to be 4 megahertz, and then 2 and 1. Right, so the first stage of the scaler is just producing the scaled clock output. Second stage of the scaler is we need some way to select these. So these are fed into a sort of multi-line decoder. So let's do a 4-line decoder here. And that is also available as a 7400 chip. Alright. And what a 4-line decoder does is it has one output. And it has 2 inputs. So that you can represent the binary numbers 0 to 3, right? 4 binary numbers coming in here. Those inputs can come from a register. And let's call this CS1, CS0, and CS1. Alright, so those two come in, and we've got one output here. What this is this is selecting which one of these inputs do we want to just translate directly to this output. And so by sending in these 2 bits over here, which come from a register, right? And the CPU can interact with this register. Keep that in mind. We get a single output here, which will be one of these: 8, 4, 2, or 1. Now in the real timer, there is a way to pick up the clock directly as well and get it here. But let's actually draw the output line this way. So this is the scaled output coming out here. And again, this is a clock pulse. Right? This goes into the actual timer counter. So this is another binary counter here. And this right here is a register that is connected to the CPU. So this is register timer 0. So now we do have the basic output here of the timer, which is we have something that's counting up at the speed we want. Right? We've gone through the 4-line decoder, picked up the scalar signal that we want, so we've got a binary register here that's counting up numbers just in order until something resets it or it rolls over back to 0 again. Then it's going to continue counting. That's all this register ever really does. Now the CPU can come in and set this register. So there is an input here from the CPU. You can set this register in your code, and we'll see that later. But what if we want the counter to do something? We need to be able to set like an alarm so that the timer goes off every now and then. One easy way to do that would be we could have another register here. So this, we could call this the compare match register. So we could set a value here from the CPU. So we could have something coming in from the CPU. Let's label CPU inputs here. CPU. So now we have a time. So we could put a number in here, like we could put 10, right? And that would cause, if the timer counted up to 10, these two things would match. Now, in order to do something at that point, and create an output that happens when these two things match, it's actually very simple. We take the output from here, take the output from here, take the output from here, and what could give us an output that's only on when two things match? That's just a simple XOR. We XOR this bitwise, and then we just, running out of room here, but we basically just take all 4 bits of this XOR and we wire OR those together. So what an XOR does is it's the exclusive OR, right? So 0 plus 0 equals 0. 0 plus 1 equals 1. 1 plus 0 also equals 1, but 1 plus 1 is off. So you see what happens is the only time that you get a 0 from an XOR is when the 2 bits match. So if you want to do a 4-bit matcher, right, what you can do here is grab the 0 or 1 off here and invert it. So if we invert this signal here, I don't know, let's draw that a line just to remind that this is inverted. What we could do with this output here is we could create an interrupt. And this would go to 1 and interrupt the CPU whenever the register and the timer match each other. So that's where you see the beauty of this come through. All you really have to do is you have a few inputs from the CPU, right? You got the scaling select, you got sometimes the counter being reset by the CPU. Your interrupt routine could do that. There's also some hardware that can reset the counter, and you can turn that on. Works similar to this. It's going to take this input and reset the counter when this comes on. Right? But we get everything that we need to get done. And all we have is these two inputs and the chip select. So now if we go to the code, we're going to see some code that basically directly sets these registers. Right? I'm going to set the scaling selector. I'm going to set the compare match when I want the alarm to go off, essentially. And then I'm going to set a decoder register that tells what should the timer activate external to itself when this match happens. Right? There's some hardware that connects this to the I/O pins that I don't think really needs explanation, and it's pretty complicated. There's a lot that you can do with that hardware, but what I'm going to do is basically just toggle the pin whenever this output happens here. Whenever my compare match timer goes off, I'm going to toggle the pin. Okay, now that we understand how the hardware works, I think the code's going to make a lot more sense. So one interesting thing about, well, the first interesting thing about this code actually is it was created in the beginning of October last year. So that means I've been noodling around with this for 6 months. And that's just kind of how geek projects go sometimes. That's the way it works. But one of the notable things about this code right off the bat is that if you look in the loop where we usually put sketch code, there's nothing here. So this does not require any sketch code really running on the CPU most of the time. Now there's some setup and stuff that definitely runs on the CPU, but once that's done, basically all that's happening is the timers do their thing and we wait for an interrupt to come in from a pin. So if you look at the top here, what I've got is I've got the interrupt library for AVR included, just because you need that. And then I've, like all good Arduino programs, I define my pins just so I don't forget what they are. I've got a couple of volatile variables here, and that's so that they're kind of safe to use in interrupt routines. These can be written during interrupt routines. Then I basically have some setup in the setup function. So let's go through that. I set the pin modes. That's just, again, good style for Arduino stuff. Then I call these functions. Setup timer 1. It says always setup timer 1. And then depending on the value of the mode pin, I either start timer 0 or I stop timer 0. Detach the step button or attach the step button. And what I want to go through here is this start timer 0 function. So remember when I explained how the hardware works, that all we need to do is set some registers and it makes things happen in the timers? That's what this code is doing. And the first time you see code like this, it is kind of mysterious because you don't know what's going on here. It looks like they're just setting a variable. But this is actually a special word here. TCCR0A is the name of one of the registers in the AVR timer system. So I can set that register, and it's an 8-bit register, and I actually set the register with a binary value. So it's very easy to see which bits are turned on here. Now, as you can see here, The first bit that is turned on here is the second one. And if you look over here, that's this one called COM0A0. And if you look in the data sheet, you find out that's one of those settings, one of those hardware settings that I talked about that tells the timer what to do. And in this case, it essentially turns on the compare match. So essentially what that register pin does is it sort of turns on that XOR hardware that we looked at before. So now something in the system can pick up that compare match output. Now, without getting too deep into the explanation here, because there is a table of these values in the data sheet if you want to look it up, WGM0001, and then down here in this other register you see there is WGM02. So together they form a 3-bit value, and that's basically 8 different settings that you can have for what happens when the compare match occurs. So the next thing that I do is basically just set that value. So I do set WGM02 also on. And then here you can see this last bit here is also on, which is bit 0 of the scaler. So you can see the scaler here in this case. Also has 3 bits of selection, allowing it to select 8 different lines. All right, remember our hardware one only had 4 bits for this, but the real scaler has 8 lines of output. So we've got the 3 bits to select, and I'm just selecting bit 1 there. So the next line of code here is basically I read the analog pin and I do some math on it, and then I assign that to the compare match register. This is an 8-bit register, so I did the math to keep this within 0 and 255. But basically this is when is the timer going to go off. How many ticks are going to happen before the compare match happens. And then this last bit here is setting the timer mask register flag, which actually activates the timer. So it's up to the viewer to kind of look up what all of these things do, but these are all basically just settings in the timer. And once you understand that they control those units of hardware that I explained in the hardware diagram, which is totally messed up now, then I think this code becomes a lot less mysterious. And you see the beauty of why they did the system this way. You see the beauty of using registers to write your code with. It's very easy to understand at least what value this register is getting set to. And you can really take advantage of some features that a lot of people don't use very often. Now, a lot of times you do use this through libraries. So if you use the Servo library for Arduino, for example, you're actually using this. They use the timers in the Servo library to generate the PWM signal. So any kind of like PWM signal that you want to generate and you don't want to have it interrupted by stuff that the CPU is doing, you're going to want to use these timers for that. So keep that in mind. All you've got to do is set the timer registers. Your compare value, your timer settings, what you want to happen when the output happens, and so on. And I think writing the timer code will be a lot easier, and I think a lot more people will take advantage of this feature, which you're paying for that in the hardware. Yeah, one of the things that you're paying for when you get an ATTiny or even an Arduino is this timer hardware. So if you don't take advantage of that, you're leaving money on the table. So I hope that's been fun. It's been fun to explain this stuff, and I hope you enjoyed it. But if you have any questions, leave me some comments. And thanks for watching Clipboard Electronics.